All right, guys. I'd like to, in this video, just go over the whole test review. So the idea behind this is you don't have to sit through a bunch of questions you don't need. Whichever problem you need help with, you can just fast forward to. You can pause it, you can rewatch it, or if you're absent, the day that we are going to go over this, you have access to this at home now. All right. So number one, we're looking for the rate of change of the average rate of change. So I see the word rate twice, and so we're looking for the second rate of change of a quadratic. And so for a quadratic function, I know it's quadratic because of the x squared. All we have to do is multiply the leading coefficient by the degree to find the rate that the average rate of change is changing. And so our leading coefficient is 6, our degree is 2. 6 times 2 is going to give us 12. So that's all we have to do on number one right there. Number two, we're given a table of values. We have to answer whether it's linear or quadratic. If it's quadratic, is it concave up or down? And then, like, why is it linear? Why is it quadratic? And why is it concave up or down? So let's start with this. To see if it's linear, we take successive differences. All we have to look at are the y's because the x's are all equally spaced. So as long as they're all plus the same number, then we're good. So let's see, the g of x values go down by 1, and then down by 3, and then down by 5. And so if these were all the same, it would be linear, but it's not linear. Okay. The next rate of change, or the next difference here, we're going to have to get from -1 to -3, we would subtract 2, and then subtract another 2. And so this tells us that the function is quadratic. And the reason would be something like the change in the rate of change is constant. You don't have to memorize this, it'll be multiple choice. But that's how we know that it's quadratic, right? The change in the rate of change is constant. Also, because the second difference here was negative, that tells us that it's concave down. Concave down. All right, that's it for number two. Number three, same question. But we see here, if we look at the g of x's, it goes up 3, and then up 3, and then up 3. So because those are all the same, this is linear. And again, it won't have concavity. It's not concave up or down if it's linear. But why is it linear? Because the average rate of change is constant. All right, that's our reason. The average rate of change here, which would actually be 3 over 4. We're not accounting for the x's here. So the actual rate of change is 3 divided by 4, 3 divided by 4, 3 divided by 4. All right, number 4, we're looking for the average rate of change on an interval from x equals 6 to x equals 20. And so all we have to do is pay attention to those two coordinate points. So we can ignore this right here, ignore that right there. And we have a formula for average rate of change. So we know that y2 minus y1 over x2 minus x1 is going to give us our average rate of change. So I'm going to call this is going to be x1 and x2, y1 and y2. All right, so we're going to go with 18 minus 4 over, we're going to subtract the x's, which is the top row, 20 minus 6. So that gives us 14 over 14, which is 1. And so that's our average rate of change on number 4. Number 5, we're looking for the average rate of change, but we're given a function this time. And so we have to have coordinate points. Right now we only have x coordinates, but we want y coordinates. So to get the y coordinates, we're going to plug those values in. We're going to find f of -1 and f of 2. All right, f of -1 means replace both x's with -1. So it looks a little confusing. It's going to be -1 squared plus 4 times -1 minus 1. Now we can do this without a calculator. We want to follow order of operations, so do what's inside the parentheses first, which there's nothing to do on the inside. Then we want to do the exponent. So here, I'm not going to cancel these negatives. I'm going to square -1. And so that outside negative stays. -1 times itself is +1 though. All right, so this first term just becomes -1. Then we multiply or divide, then we add or subtract. And so 4 times -1 is -4, and we have that -1. If we add or subtract these together, that's going to lead to -6. Now, what does this represent? It's a coordinate point. When I plugged in -1, I got -6, and so that's our coordinate point right here. Same thing here. If I plug in that 2, I get -2 squared plus 4 times 2 minus 1. I'm going to do the exponent first. So I'm going to square this. I don't move the negative inside. It's on the outside. 2 squared is 4. So this is -4 plus, I'm going to go ahead and multiply 8 minus 1. That's going to just give us 3. And this is also a coordinate point at 2, 3. 2, 3. All right, so now we can take our coordinates and we can plug those into our formula. So I'm going to say this is x1, y1, x2, y2. So y2 minus y1 over x2 minus x1, 2 minus -1. Both of these turn into pluses, so 3 plus 6 is 9, and 2 plus 1 is 3. 9 divided by 3 is 3, and that's our answer here to the average rate of change. All right, so number 6 is a conceptual question. We're told that the average rate of change is 3. We want to know how much the function increases over an interval from 2 to 7. Remember, average rate of change means slope. So I'm telling us the slope is 3 over 1. Now, we don't have any coordinate points, but imagine with me that we just start at 2, 0. We can start anywhere. I'm going to start at 2, 0 though, because that's the beginning of the interval is x equals 2. These are both x coordinates, all right? So I don't know the y coordinate. I'm just saying that it's 2. If the slope is 3 over 1, what that means is we go up 1, 2, 3, and over 1, and there's our next point. Okay? So up 3 over 1. Then we continue to do that. So I go up another 3, 1, 2, 3, over another 1. Over another 1. Same thing, we just keep going with this. And so from here to here, right, it increased by 3. It went up 3 over 1. Then we went up another 3 over another 1. Now, you could draw out the whole thing here, but let's think about this. We're going to go from 2 to 7. So we're at 2, 3, 4, 5, 6, 7. So that would be 5 times that we're going to go up 3 and right 1. Well, how much does the graph increase? Well, we're going to increase by 3, a total of 5 times. The graph is going to increase by a total, therefore, of 15 over that interval. Right, there's 5 times from 2 to 7, right, to 7 minus 2. And each time we go up 3 and over 1. And so 3 times 5 gives us the amount that we increase over that interval. All right, number 7 is asking for the rate of change of the average rate of change. So that's our second rate of change. And remember, for a linear function, the first rate of change is that number right there, -3/2. That's the average rate of change, or the slope. But the second rate of change is always 0. That's the rate that the average rate of change is changing. All right, so that's our answer on this one, just 0. All right, number 8 is really just having some of our vocabulary memorized. We've got a table here that's discussing the rate of change of a function. But our questions don't talk about the rate of change. They talk about the actual graph. And so what I want to do is just change these questions so that they're referring more to the graph up here. All right, so question A, when is the graph concave down? Well, if you remember from class, we learned that this means the same thing as asking when the rate of change is decreasing. That's our question here. All right, when is the rate of change decreasing? Well, the only time that the rate of change is decreasing is in this first interval, So we're going to answer -3 is less than x is less than 0, and that's our answer right here. Okay, there's nothing to it. We don't have to sketch a graph. We don't have to know what it looks like. We just have to be able to translate what that means. Now, the graph is both decreasing and concave up. Decreasing, concave up. Again, since this is talking about the rate of change, we have to know what this means for the rate of change. The rate of change is going to be negative, and concave up means increasing for the rate of change. So now we're looking for when is the rate of change both negative and increasing. That only occurs right here in this middle column. So that's going to be from 0 to 4. So 0 is less than x is less than 4, and that's our answer right there. All right, number 9. So we're given a polynomial in factored form, but in order to get the degree and the leading coefficient, we need this to be in standard form. Now, it would take a while to distribute all of this. So what we want to do is just figure out what the highest order term would be. To get the highest order term, I'm going to rewrite 3x plus 1 squared as 3x plus 1 times itself. 3x plus 1. And then I'm going to take the highest order, that's the biggest exponent from each grouping, and I'm just going to multiply those. So we're just taking the biggest exponents, 5x times 3x times 3x. So 5 times 3 times 3 is 45. And x times x times x is x cubed. Okay, so this would be the biggest exponent if we were to distribute out everything. Our degree is always our biggest exponent in standard form, so that would be 3. And the leading coefficient is the number in front, so 45. All right, that's number 9. Number 10, I'm going to split this up over 2 slides because there's a lot of questions here. So, first question is asking for the zeros. So zeros occur anytime the graph either passes through or bounces off the x-axis. All right, so we have 2 zeros. We're going to write them as x equals a and as x equals e. All right, next question is asking for the relative maximum. So relative maximums can occur at endpoints, which we don't have any on this graph, but they also occur at turning points. So there's a turning point down here, but that's a minimum, and a turning point right here. It's okay that it's a 0, it doesn't matter. It's still going to be x equals e. All right, C is asking for the point of inflection. There's no way to know for sure exactly where it is on a graph, but we can tell it's about right here. This graph starts off opening up, and then somewhere in here it switches to opening down, right? So about where D is going to be the point of inflection. And this graph would only have one point of inflection. All right, D is asking when the graph is decreasing, not the rate of change, but the actual graph here. So let's see, I'll highlight this in yellow. So we're looking for when the graph is decreasing. We go from left to right. As we go from left to right, this graph is moving down. Okay, and then it goes up, so it's increasing, and then right here from the maximum, it starts to decrease again. Now, how do we put this in interval notation? Well, we want to list an interval of x coordinates. Okay, and so this graph is going up and left forever towards the coordinate point -infinity, positive infinity. And then over here, it's going towards the coordinate point positive infinity, negative infinity. But again, we only care about the x coordinates. So I'm going to take this x coordinate and this one. They'll go in our answer, but the y coordinates will not. So my first interval is going to go from x equals -infinity, which I'm wrong. Infinity always goes in parentheses. 2, it stops decreasing at x equals b. Then it starts decreasing again at e. And it stops when we get to x equals infinity. And so that would be our interval notation right there for when the graph is decreasing. Now, when's the graph concave up? Well, we talked about this a little bit earlier, that this graph is starting off opening up, but it stops right here, okay? And so the x coordinates would be from -infinity to d when this graph is concave up. -infinity to d for our answer there. All right, this next part is asking when the graph is both increasing and concave down at the same time here. So when is our graph increasing? Let's go with green here. It's increasing in this section. Okay, but it's not concave down the whole time. The first half of this is concave up. This portion right here, the graph is concave down and the function is increasing. So we're going to answer from D to E. D to E, like that. All right, same graph. We just have more to go through here. So G is asking when the rate of change is positive. Well, this is the actual graph, the literal graph, not the rate of change, right? So let's change that question. It's not when the rate of change is positive, or let's make it when the graph is increasing. Okay, and again, it means the same thing. It's just we have the graph here. So we want to see when the graph is increasing. It means the same thing as when the rate of change is positive. Well, we just talked about when the graph is increasing. It's increasing in this section, right here. Right, from B this time all the way to E. From B to E. Oh, put that in the wrong spot. From B to E. All right, there we go. All right, now this one, rate of change decreasing. We have to know that really means when the graph is concave down. Concave down. All right, so when's the graph concave down? Well, it starts at D and it never stops. So we're going to say from D to infinity. Again, the x coordinates are what we're listing here. When is the rate of change both negative and increasing? That means when is the graph decreasing and concave up. So the rate of change is negative when the graph decreases. The rate of change is increasing when the graph is concave up. So let's see, when is the graph both decreasing and concave up? Well, let's look at the part of the graph where it is concave up. So right here, our graph is concave up till right there. And it's going to be decreasing until the minimum. After that, it's no longer decreasing. All right, so it's going to be just this portion right in here. So we would answer that as being from negative infinity to B. All right, and lastly, when is the graph increasing at a decreasing rate? And so a little confusing on this one. Switch back to white here. This is asking about the graph. This is asking about the rate of change. So really what this means is that the graph is increasing, and the decreasing rate means that the graph is concave down. That's what we're looking for here. When is the graph increasing and concave down, which we already answered, I believe, at one point. But let's see, increasing and concave down is this little section right here, okay, from D to E. D to, and that's it. All right, guys, thanks for watching. Stay flawless.